Next, we need to cover the basics of broadband RF distribution in and to the home, including external sources such as satellite, cable, and off-air signals. The distribution of internal sources such as DVD players, modulated AV sources, and cameras, coax cable types and characteristics, direct broadcast satellite systems, and off-air antenna systems. A broadband RF network must support the distribution of external sources, such as cable service signals, off-air signals, and satellite signals. It must also support the distribution of in-home generated sources, such as VCRs, DVDs, and other entertainment program sources, cameras, and computer-generated media. Let's start with an overview of each external source, starting with traditional cable service. The cable television industry uses a standard channelized frequency allocation on their distribution system. Downstream channels start at channel 2 and go up beyond channel 125. You've got a copy of this table in your workbook, so look at it. The table gives the channel allocation frequency and visual carrier frequency for each channel for 3 band plans: the EIA standard plan and the older IRC and HRC plan. Cable companies were required to begin using the EIA standard frequencies prior to 2000. By using digital compression techniques, cable companies can squeeze 6, 8, or more digitized NTSC channels into a single 6 MHz channel space, greatly expanding their potential channel capacity. But it requires a digital set-top box to convert those channels back into NTSC analog format. The amplitude of cable channel signals, as well as all RF signals we'll be using, are expressed in dB or decibels. They're used to express the ratio of any two values, such as power or voltage, and greatly simplify calculating gains and losses of RF systems and components. For example, if we know the signal into an RF amplifier is 1 volt and the output is 2 volts, we know by this formula that the amplifier has a plus 6 dB gain. Likewise, if we know the signal into a length of coax cable is 1 volt and the output at the other end is 0.3 volts, we know the coax has a loss at the frequency of the signal of minus 9.5 dB. By convention, the minus sign means a loss. This is a table of common signal level dB gains and losses. Notice that increments of 20 dB voltage gain or loss is equivalent to powers of 10 increase or decrease. Plus 20 dB is equal to a 10 times increase. Plus 40 is equal to 100 times, and so on.
Fortunately, when designing an RF distribution system, the dB gain or loss of a particular component, like an amplifier or the coaxial cable, is given to you by the manufacturer. So all you need to do is add them together for each path through the system.
For example, if we know that the loss of a brand of coax cable is 8 dB per 100 feet, then this system, with 100 feet from the cable service NID to an amplifier, with 10 dB of gain, then another 50-foot length of coax to a TV, will have an overall gain or loss of minus 8 and plus 10 and minus 4, or a total of minus 2 dB of loss. So if we know the input signal level, we can easily figure the output signal level.
While dBs express a ratio, absolute cable company signal levels are typically given in a unit of measure called a dBmV, or decibel millivolt. The MV after the dB means an absolute signal level reference to 0 dBmV. 0 dBmV is a standard reference level of 1 millivolt of the visual signal level across a 75 ohm resistance. 75 ohms because the cable system is built around 75 ohm impedance cables and equipment. A 3 dBmV signal has a level of 1.41 millivolts across a 75 ohm load, and a 10 dBmV signal has a level of 3.2 volts. Likewise, a minus 6 dBmV signal has a level of 0.5 millivolts. A minus 3 dBmV signal applied to an amplifier with a 10 dB gain would result in an output signal level of plus 7 dBmV. We'll talk more about amplifiers and amplifier gain shortly.
The cable company's visual signal level at the NID or connection point at the house should not be anything less than plus 3 dBmV on any channel.
Now, the signal level in the house at the point of connection of the customer's equipment should not be less than 0 dBmV on any channel. Now, the only upper limit given in Part 76 is, I quote, a maximum signal level such that signal degradation due to overload of the subscriber's receiver does not occur, or something like that. Now that's usually a maximum of plus 15 dBmV, and ideally in the range of 0 to plus 10 dBmV. This is also the range that the cable tuners in televisions are designed to handle.
RF signals can be easily measured utilizing a portable signal level meter like this. This unit will make any number of key measurements on any cable signal or off-air signal with an input range of minus 35 to plus 60 dBmV.
All broadband services use coaxial cable. Like TP cable, coaxial cable comes in various performance ratings established by cable standards organizations.
The coaxial cable is constructed very differently from twisted pair. It consists of a center conductor surrounded by one or more shields. The cable is divided into numbered series with common characteristics in each series.
Now you can think of coax as sort of a two-wire cable where one of the wires has been flattened out and wrapped around the other one. Now the center conductor is usually 18-gauge solid copper or copper-clad steel for strength. The shields are separated from the center conductor by a dielectric insulation, typically foam polyethylene. Now the cable may have a single foil or braid shield or a combination, such as this foil, braid, and foil. A quad shield cable will have an extra braid. The inner foil is used for shielding as well as being one of the signal conductors. Now a braid does provide a shielding, but it's primarily used for the cable's strength. Extra foils and braids provide extra interference protection and extra strength. And finally, an outer PVC jacket covers the shields.
The most common coax cable for residential use as recommended by the TIA standard is Series 6. The designation for Series 6 cable is RG6. RG6 has a very low signal loss. It's typically used for all broadband RF application infrastructure wiring in the home, such as cable television. It comes with 2, 3, or 4 shields, like this: an inner foil, a braid, foil, and braid.
This chart, also in your workbook, gives typical loss figures for RG6 for 100 feet at frequencies up to 1000 megahertz. Remember, loss is frequency dependent, increasing with increasing frequency. It's also additive. 200 feet has twice the loss of 100 feet, 50 feet has half the loss, and so on. The TIA recommends using either 3 or 4 shield or quad shield coax as it's called. We'll be using this quad shield RG6 for all of our RF broadband wiring. RG6 coax uses F-style connectors developed by the cable TV industry. The mating jack is a barrel-style connector. This means the cable in the wall also has an F connector plug, so there's only one type of connector to apply to the cable. F connectors are available for 2 and 3 shield RG6 and for quad shield RG6. The most common F connector uses a threaded hex end and a barrel designed to be mechanically applied to the cable. The most common one-piece connectors are the hex crimp and compression crimp. These incorporate an integral crimp ring for strength and ease of installation. The most common two-piece is the snap and seal connector, applied with a special tool. Newer versions of this connector have the plastic sealing ring already in position on the barrel. Before we leave the subject of cable, we need to cover NEC cable listing requirements. The NEC requires that all cables used in a building have a rating identifier marked at regular intervals on the jacket to identify if the cable meets safety requirements for various spaces and cable run applications. Any low-voltage cable you use, such as security, control, or speaker cable, must have at least an NEC Class 2 or Class 3 cable marking. Now, this will be the letters CL2 or 3, followed by another letter to identify the allowed application. Now, P is for plenums, ducts, and air handling spaces. R is for use in risers or vertical shafts that penetrate more than one floor. G, or no letter, stands for general purpose, meaning locations other than plenums or risers. And X is for residential, designated for single and multifamily dwellings and raceways. Any of these designations are acceptable for residential applications. Copper communications cable, such as TP or coax, may have a CL marking, but will more typically have a marking such as CM followed by another letter. The C stands for communications, the M for multi-purpose, and the third letter is the same designation as for the CL markings. Now, fiber optic cable has a similar designation. The OF stands for optical fiber, of course, followed by either N or C, non-conductive or conductive, meaning there's a metal strength member in the cable. And then the last letter is the same as for the copper conductors. There are a number of good reasons to incorporate off-air antenna signals into the RF distribution system. First, and maybe most important, it's free. And second, to receive new digital television signals. Now, nearly all broadcast television stations have got to begin broadcasting digital television, or DTV, by 2006, and most already have. Now, with a good off-air antenna installation, there's absolutely no reason why the picture quality from off-air can't be just as good as that from cable or satellite. This chart, similar to the one we saw for cable channels, shows the UHF and VHF frequencies for each 6 MHz TV channel. Notice that the VHF channels are divided into two groups, channels 2 through 6 and 7 to 13, sometimes referred to as the low and high VHF bands, at 54 to 86 and 174 to 216 MHz respectively. Between these bands lie a number of other radio services, such as FM stations between 88 and 108, and aviation band between 108 and 136 MHz. UHF channels 14 through 69 occupy channel frequencies from 470 to 890 MHz. Since off-air and cable channels above channel 13 use different frequencies, television or other receivers have to have tuning modes that select between cable or off-air frequencies. RF broadcast signals need to be captured by an antenna designed for the range of frequencies in the VHF or UHF band that the customer is interested in receiving. Now, if you only need to incorporate digital television signals, then you only need to select a good quality UHF antenna. Most antennas are designed to receive either the VHF band, the UHF band, or a combination of VHF and UHF band. To receive a good quality, noise-free picture, the antenna needs to deliver a signal level of 0 dBmV to the receiver, similar to a cable signal, although most receivers will give an acceptable picture down to about -10 dBmV. To deliver this signal level, the antenna requires a certain gain. The amount of gain required is dependent on the line of sight distance to the desired station's transmitting antenna and the power transmitted by the station. In general, the gain of an antenna is dependent on its size and the number of elements. Now, due to the smaller size of the elements, UHF antennas can utilize more creative shapes to achieve high gain. Selection of the right antenna for the job has been made a lot simpler by the Consumer Electronic Association. Their antenna website will help you select the best antenna type for a particular location. We'll demonstrate the site and antenna selection and installation later in the course. In this part of the course, we're going to cover direct broadcast satellite systems. Now, these systems are also referred to technically as Ku-band DBS systems, due to the designation of the 12 GHz downlink spectrum it uses as the K sub U or Ku microwave band. Source television signals are converted to a digitally compressed MPEG-2 data stream. The data stream is transmitted on a 17 GHz uplink carrier to a geostationary satellite. In the satellite, the received signal is converted in a device called a transponder to a 12 GHz downlink carrier and broadcast over a wide geographic area visible by the satellite. The signal is received by a small high-gain dish antenna pointed at the satellite and connected to a specialized receiver. The receiver converts the signal from an MPEG-2 data stream back to the original analog form for viewing on a local television. Satellite service in the U.S. seems to be constantly changing. But at the time we made this course, there were two major suppliers of DBS service: DirecTV, owned by Hughes, and the Dish Network, owned by EchoStar. The dish receiving antennas for both providers look similar, but differ in how they convert arriving signals for the receiver. DirecTV antennas are equipped with 1 to 3 LNBs to receive the network signals from satellite transponders at the 101, 110, and 119 degree orbital positions. New Dish Pro antennas are equipped with 2 LNBs to receive the network signals from satellites at the 110 and 119 degree positions. The LNB, or Low Noise Block Converter, converts the received 12 GHz band of downlink signals to an intermediate frequency band from 950 to 1450 MHz. Power for the LNB is supplied by the receiver over the same coaxial cable used to feed the signal to the receiver. For DirecTV LNBs, the voltage level is used to select the odd or even transponder channels, carried on the left or right-hand circular polarized signals, respectively, from the satellite. Dish Network LNBs incorporate a European standard called Digital Satellite Equipment Control Technology, or DISEC for short. It allows two-way signaling between the LNB and the receiver. Now, both even and odd transponder channels are output at the same time using 2 blocks of intermediate frequencies, 950 to 1450 and 1650 to 2150 MHz. There are 2 approaches to installing multiple receivers in the same home. The obvious is simply to install a separate satellite dish antenna for every receiver. The other approach is to allow one antenna to be shared by multiple receivers. To do this typically requires a device called a multi-switch. Basically, a multi-switch allows every receiver to view any transponder channel on any satellite that the antenna can see. A typical DirecTV multi-switch receives the polarity voltage and a tone from each receiver and switches the appropriate left or right channel from the correct LNB to that receiver. This requires a dual output LNB. The LNB has 2 connectors that output the left and right-hand polarized transponder channels at the same time. These are very common on new satellite antennas. DirecTV multi-switches typically have 4 inputs, the left and right-hand outputs from 2 LNBs, and 4 to 8 outputs for receivers. Multi-switches for the Dish network have 2 inputs for the dual LNB that supports both primary satellites, and an extra input for a secondary dish. This model supports 4 receivers, but is cascadable to support up to 12 receivers. Since multiple receiver installations are so popular, many manufacturers of multi-LNB dishes are building them with multi-switches built in. This 3 LNB DirecTV dish from Turk has a multi-switch built in which will support 4 receivers. This Dish Pro quad output dual LNB allows up to 4 Dish Pro compatible receivers to share the same LNBs. Unfortunately, multi-switch and LNB designs are constantly evolving. Even the satellite and transponders change. So make sure and check that the LNB and multi-switch technologies you're using are compatible and recommended by the services you're using. Where is Richard? Now that we've covered sources, let's cover how they're combined in the distribution device. Now, incoming off-air cable service is split to support branch cable runs to outlets throughout the home. Let's first cover some component characteristics you'll need to know, starting with splitters. A splitter divides an input signal equally between 2 or more output ports. They typically come in 2, 4, 6, and 8-way versions. They're also referred to as a combiner, since they're bidirectional and can be used to combine 2 or more signals. They may or may not be DC passing, that is, they may pass a DC signal either for power or IR signals over the coax. Because they divide the signal, they divide the power or amplitude between the outputs. The outputs of a 2-way splitter are typically 3.5 to 4 dB less than the input. Your workbook has a table of the attenuation for 2 to 16-way splitters. Splitters also have a frequency range specification over which they operate. This can range from as little as 5 to 54 MHz up to over 1,000 MHz. When a source signal, such as cable or off-air, is split to 4 or more destinations, an amplifier should be used between the sources and the splitter. The gain of the amplifier is chosen to overcome the signal loss in the splitter and coax cable runs to outlets. Amplifier gain is a measure of how much the amplifier amplifies and is always given in dB. A 10 dB amplifier will increase the input signal amplitude by 10 dB. Gains of from 5 to 20 dB are typical for broadband RF amplifiers. Amplifiers come in both variable gain and fixed gain models. Fixed gain amplifiers are typically available for 10, 15, and 20 dB gain. In residential applications, the distribution amplifier is often combined with splitters in one package, since the two are so commonly used together. One input is amplified to several outputs. To support cable set-top boxes, many distribution amplifiers have a 5 to 50 MHz return path built in to allow upstream signals from the set-top box back to the cable company's central office. The opposite of an amplifier is an attenuator, used to lower the amplitude of a signal. They typically come packaged in a barrel shape marked with the dB attenuation level. You'll find these commonly in 3, 6, and 10 dB versions. You can screw them together to achieve any amount of attenuation you need. Structured cabling systems should also incorporate the distribution of in-home generated video sources, such as the output of DVD player, satellite receiver, or a camera, so they can be viewed on any television in the home. Distributing in-home sources requires installing an additional coax cable and jack and outlets where DVDs or other sources are located. The downstream cable from the distribution center to outlets that carry cable company or off-air signals is referred to as the external cable. The added upstream cable is referred to as the internal cable, since it carries in-home RF sources to the distribution center for redistribution on the external cable. At the distribution center, the internal cable runs are combined, mixed with the external signals from off-air or cable service, and split as before to all external outlets. Let's take a look at how this works to view a movie from a DVD player in the family room on a TV in the master bedroom. The DVD player audio and video outputs connect through an RF modulator to the internal coax connector. The television is connected to the external coax connector. To view the DVD player, the TV is tuned to the channel set on the modulator. Modulators are really small television stations that broadcast a baseband audio and video source onto a cable or off-air television channel. They have baseband audio and video inputs and an F-connector RF output. They also come in a wide range of sizes, from single-source single-channel to four-source four-channel models. All the modulators you'll be using are frequency agile. That is, you can select the output channel in either the cable or off-air channel range. You need to do this to set the modulator channel to one that's not used by local off-air cable channels. Now, to make modulators relatively inexpensive, they transmit both sidebands of a television picture, leaving out the expensive circuitry required to remove the lower sideband. This means they require a 12 MHz bandwidth, 6 MHz at the channel they're set to, and 6 MHz of the lower channel. Therefore, if you're using multiple modulators in a system, or combining modulator outputs with cable or off-air signals, you need to leave one unused channel between the selected modulator channels. So if a modulator is set for channel 80, for example, it will actually use channels 79 and 80. Modulator output levels are usually high, typically 25 to 35 dBmV. This comes in handy since they're usually placed in the internal path of a coax distribution system where losses are high before reaching a distribution amplifier. Next, let's cover filters, a very common component in RF distribution systems. They're used to pass one range of frequencies while blocking others. The most commonly used in residential applications are the low-pass and band-stop. The low-pass filter passes signals below a specified frequency and blocks signals above that frequency. Filters are specified by their pass frequency or pass channels, usually given as cable channels. Real-life filters are not perfect. The attenuation increases gradually in the block part of the spectrum, reaching a maximum of -30 or 40 dB. Low-pass filters are typically used with cable or off-air service to block frequencies above a certain channel, so that in-home modulators can be inserted into the channel space above the blocked channel. For example, this Channel Vision low-pass filter is rated to pass below 648 megacycles or cable channel 105. The attenuation slope is about 4 channels or 24 megacycles, so the closest inserted channel should be 109 or above. A band stop filter blocks a range of frequencies. These are also called notch filters and can be used to remove one or a group of channels. This Channel Vision notch filter blocks cable channels 61 through 68, providing 4 channels, 63 through 66, for use by modulators. A diplexer is a combination of a high-pass and low-pass filter in one package. They're used to either combine or split 2 signal frequency ranges. The most common example is this diplexer that will combine the output from an off-air antenna up to 850 MHz with the output of an LNB between 900 and 2150 MHz. They're typically used to allow one coax cable to carry both off-air and satellite LNB signals, combining them at one end and splitting them back out at the receiver. Distribution panels come in many sizes and configurations to support different size houses and applications. Now they have to contain all of the network modules and support equipment for each network type, including things like power supplies and power strips and accessory equipment. Manufacturers typically provide some mechanical means to mount the modules and equipment where you need them. This particular manufacturer has a grid of holes in the back of the panel, and each module has these little plastic snaps. Now the snaps line up with the holes in the back, and you just snap them in to mount the module at any convenient location. Now the size of the enclosure you need depends on the size and the number of modules you need to support your applications. So once you've determined the number of outlets and the applications you need to support, you work backwards to determine the modules and then the enclosure to contain them. Now we're going to cover how to design the networks and plan the enclosure and what goes inside in part 2 of the course. And speaking of part 2, looks like Richard's finally back. Hey, let me give you a hand. Well, we just finished part 1, and now it's time to cover planning.
Good. I guess to do that, we'll have to take you back a few days to the real beginning and show you how Grayson and I planned this job.
An excellent idea. Glad you got the pizza.
I got what I like. I hope you like anchovies.
I love anchovies. Let's just not kiss.